Hello and welcome. You are going to look at an overview on inverse functions. In this lesson, you will learn how to find inverses of functions graphically and algebraically. Let's go ahead and do a quick revisitation on functions. Let's take a look at the definition so we make sure we know what those are, because they'll have to do with inverses as well, and the different ways we can find them. Function definition, it is a relation, so meaning some sort of set of points, if not even just one point, in which each element of the domain, the x values of coordinate pairs, is paired with exactly one element in the range, y values. So if you have something that is a function, it can either be identified by finding the domain and range with the equation or the rule. So basically, you start plugging in some values for x within your domain. You can only get one value out for y for any of those x's, not all of them. Any one of them can fail it. Tables, you can use a mapping diagram or any sort of tables in particular. Anything that can show that x is pointing to more than one y, that would be an issue. Or finally, the vertical line test, which pretty much basically shows it in a nutshell. I have a parabola or something here. If I draw a vertical line at any one point here, it should only be hitting one point uniquely and specifically. If it passed two different points anywhere, then it's failing that vertical line test, and then you have more than one element in the range paired with just one element in the domain. And finally, function notation, we can see it as f of x or g of x or h of x, whatever it is equal to your y value, which is our dependent variable. So what we're going to do a lot is we will isolate our dependent variable and solve for it because it's something that we know how to graph, and we state things as functions in terms of the y's being the guys that go up and down on the graph over here, and x's are left to right, etc. So the reason why, although I should probably change this now to what's his name? Actually, I don't remember his name, but this is Brandon Routh here. And Henry Cavill. Henry Cavill's our new Man of Steel, Superman. The idea is this Superman guy, he could do anything. He's a function where he can fly wherever. His domain and range is unlimited. But he can never be in two places at one time. That's one of his biggest, I won't call it a pet peeve, but that's one of his greatest weaknesses outside of kryptonite. He can never truly save everybody at any one time. And there are, you can't save people from heart attacks either. But basically, he can't function like that. If the best of us can't do that, how can we do it? We can't. At any one time, we can only be at one place. But let's go ahead and take a look at what an inverse relation or function is. We'll get to it in just a moment, starting by taking a look at original functions. These graphs, what their domain and range are, and they're already graphed for you. The first one here is a linear equation, y equals 1/2 x plus 4, where if you don't know how this is necessarily graphed, you start at 0, 4, because when x is 0, this goes away, y equals 4. And this 1/2, this slope says every time x increases by 1, your y value increases by 1/2. Although we don't like to say that because we don't like to work with fractions that much, so we save ourselves and we say, okay, instead of going up 1/2 each time, let's just go up 1 each time. But to keep that consistent rate, if you go up 1/2 every time you go up 1 over 1, then you'll go up 1 every time you go over 2. Up 1 over 2, up 1 over 2, and you have your graph. This one goes on forever in the x direction to the left and to the right. I could put arrows there. The original graph did not, but it implies continuity forever. So domain asks you, what values of x could I substitute into this equation where I get a value out for y? And the answer is there are no restrictions, so you can do all real numbers. I can do negative infinity and positive infinity and 0. There are no jumps, asymptotes, any issues of that nature. We can span forever in the left and right direction without any breaks. The range is basically saying, given all the different values in your domain that you can plug in, what are the different y values that you can possibly get out? And normally what you want to do is span at negative infinity, check the extreme minimum for x, and figure out how low it goes or how high it goes, and also go to the extreme maximum. And at times, like this linear equation, that's where you'll get your true answer. Like all real numbers for this case as well, because this will forever go downward this way, and it will forever go upward this way. So these are both all real numbers. Now, that doesn't mean that you hit every real number on this thing. Let's take a look. We don't hit that one. But we have an infinite set of solutions such that x at any one time could be any real number, and y at any time given x could be any real number. There are no limitations to what x and y can be. Y equals x plus 2 quantity squared. If you want to look at this in vertex form truly, there's a 1 out there as the stretch factor, and your k value is 0. So our vertex is going to be at negative 2 comma 0. Okay, so we start there. With a stretch factor of 1, because this is squared, every time you go over 1, you'll go, sorry, not every time. If I go over 1 from the vertex, I'll go up 1 squared. Over 2 from the vertex, go up 2 squared. Over 3 from the vertex, go up 3 squared, etc. Same with the left side. You square negative 1, you get positive 1. You square negative 2, you get positive 4. You square negative 3, you get positive 9. And your graph goes up that way forever. So for this particular case, the domain, it does go up forever because you can keep plugging in values for x. You'll get a value out for y. No issues with these x's right here. You can choose any real number. You will get all real numbers for x in this case. The range, as I said before, it might be beneficial to look all the way to the left in the x direction and see where you go. If I go forever to the left, I'll be ending up here. And check the max. I go forever this way, I'll end up here. So it looks like this can go on forever upwards. But you have to make sure that you check any and all critical points on this. And a quadratic has a vertex. So find that vertex, and we can find it right there. Locate, because that's the bottommost point that you will get, at least for a vertex that's facing up, or for a parabola that's facing upward. And this point is at the x-axis. The value of y at the x-axis is 0. For range, you're asking how high or low it can go. And we're saying that y can be 0 or greater than it. Okay, number 3, y equals the square root of x plus 3. The graph is as follows: stretch factor of 1, k value of 0. So we start at, it's a starting point. I still don't know to this day. I keep mentioning it, but I don't know if it's called a vertex. And that's sad for a math teacher to be saying that, but you know what? I should research that. If this is truly a vertex, it's a starting point for sure. But every time you displace your x from 1, you'll go up the square root of 1 in this case. Displace 2 over, you'd go up the square root of 2. I don't know that value enough to graph it. Square root of 3, don't know that value either, but the square root of 4 is 2. Square root of 9 is 3. And we keep going. Square root of 16 is 4. And our graph goes forever in this direction. Now, it stops right here. There is no arrow right there. It doesn't go forever downward. No, in fact, this is the starting point because there are restrictions in the domain for this problem. Why? Because for x, you do not want to pick a value for x inside here that when you add 3 to it, you get a negative number. Okay, there are such things as imaginary numbers, but they are not graphable on this real number plane. So x plus 3 has to be 0 or positive, so we can establish that right here. Therefore, if you subtract 3 from both sides, x has to be greater than or equal to negative 3. Anything that is less than negative 3 becomes an issue for our domain. We will not get points out. So whereas opposed to these two have domains of all real numbers, this one is limited in such a way that you can only be negative 3 or greater than. Now, as far as the range goes, again, take a look at your graph here. It's important to go as far left in your domain as possible, in this case, negative 3, and you get 0 out. As far right as possible, like positive infinity, you'll get positive infinity out for y. And any other critical points in between, it doesn't seem like there are any, but just taking a look at the graph, you can see that y goes up forever and limits itself to just being greater than or equal to 0, much like problem number 2. So there you are. There's your range for that one based on your domain. Range is hard to find with just the equation. You'd really have to see a graph or plug in some points or know something about the behavior of that function to say something about it. And that's all I got there. So this didn't help you answer what an inverse relation or inverse function is, but we begin by looking at this. I'm going to revisit these after I do another example and show you what an inverse is and say how we can take the inverse of these guys. By the way, domain and range was super important for what I'm going to talk about. Okay, so now we're going to start taking inverses here, and we do it by reflecting points across the line y equals x. Now, y equals x is this line right here. It's y equals 1x plus 0, y-intercept of 0, go up 1 over 1 like that. It's a diagonal line, essentially 45 degrees, even though this graph is just a little bit stretched here. I'm going to plot some points here. 1, negative 1. 2, 0, 3, 1, and 4, 1. And what I'm going to do is I'm going to reflect them across this line. Now, if you tilt your head with me 45 degrees so that this line appears like it's going up and down, like my marker appears like it's going up and down, and I'm doing it right now, what I want to do to reflect across is go perpendicularly to it, find out whatever distance away I was from it, and match that on the other side. Okay, that's what a true reflection would be. So you've done that with geometry, reflections in geometry. Now, I'm not going too specific in it. This isn't 1 unit away, but it is one whole corner set away. So this is also one corner set away right here. This is a reflection across here for this point. Here's the pre-image, here's the image. This one also has the same ordeal, but going up right here across y equals x. And again, if you're looking sideways, you can see what I'm talking about with it. Even though this graph is not perfectly squared off, you can still get the idea of, oh yeah, that looks kind of mirror-like. This one is the same way right here. And then this one is one corner shot away, half of one away, so like 1.5 over. So if we got 1/2 and 1 over right here, I would end up there. That's a small piece of reflecting for you just on a visual sense, and it doesn't always work out that way very easily. But what you could also do is take a look at what this table here shows us. This is for these points, 1, -1, 2, 0, and 3, 1, and 4, 1. Let's take a look at our new points that we just found here. Our new x value, our new xy value for this is -1, 1. Our new xy value for this is 0, 2. This is 1, 3. And this is 1, 4. Now, what relationship do you notice with these table values? Hopefully, you got some connection that, I'll take a look. Every element in my range, in my original function, or in my original relation, became an element in my domain, in my new relation. Right there. 1, 1, -1, -1. 0, 0, 2, 2. 1, 1, 3, 3. 1, 1, 4, 4. Now, that's always going to happen. If I'm reflecting across y equals x, what we're doing is we are swapping our x's with our y's. This is finding the inverse of the relation. Okay? If we find the inverse of any relation or function, we are essentially swapping x's with y's. So while I did this kind of convoluted reflection right here that was a little troublesome, you don't have to do that. You could say if this point is 1, -1, then this point is -1, 1. And same with this being 2, 0. Now this is 0, 2. What if you had a point on the graph that was 4, 4? You swap y and x, what do you get out? 4, 4. You get the same thing. So it's kind of cool that you can, and you could draw a smiley face with this. Oh, you can do whatever you want. No, but the excuse me. But the idea is that whatever was x becomes y. So this y equals x means that any point, if your function or your relation goes through here, your inverse would intersect at that exact same point as well. It would have to. But before I go over to the other page, I'm going to also look at what this syntax here says. This says the inverse of the function of x. So if your original set, if your original relation is a function, taking an inverse function here will look like this. It's like f to the -1st power, but I wouldn't treat it exactly like that, exactly like negative exponents are. There's a little bit of difference as far as what we're going to do. So let's go ahead to that next slide. Let's find the inverses of those previous examples like I was talking about, as well as their domain and range. Remember, every x value becomes a y value and vice versa. We will look at graphs to confirm. So the original equations that I had last time here looked like y equals 1/2 x plus 4, y equals quantity x plus 2 squared, and y equals square root of x plus 3. What we will do is find their inverses. Now, when I find the inverses, any x value becomes a y value, and any y value becomes an x value, including in their original equations. What was a y here is now going to become an x. What was an x here is now going to become a y. Boom, I have now created the inverse function. Here it is. However, if I wanted to make it look like inverse function, if I wanted to make it look like inverse function, boom, of x equals, I need to make this say y equals something, because I'm going to swap this out for y, because this is another y value. So to solve for y, I'm going to subtract 4 from both sides. Well, first I'm going to move this 1/2 y over. subtract 4 from both sides, then multiply both sides by 2. Okay, so therefore y equals 2x minus 8, and also inverse function of x equals 2x minus 8. Okay. I'm just going to move on to numbers 2 and 3 and solve these first, then I'll look down at these graphs here. Number 2, y equals x plus 2 quantity squared. To solve for y, to find the inverse, you swap x and y. To solve for y, I must now take the square root of both sides. Like so. Okay. Now we're going to get y plus 2 equals, be careful here, plus or minus the square root of x. Subtract 2 from both sides, you'll get y equals plus or minus the square root of x minus 2. Now this minus 2 doesn't get affected by this plus or minus. That only has to do with the square root of x right there. So to better write it, inverse function here is plus or minus the square root of x minus 2, like so. Okay. Third one, y equals square root of x plus 3. Swap x and y to find its inverse. We have found it, but now let's write it in terms of y equals. Square both sides right here. And we'll get y plus 3 equals x squared. Therefore, y equals x squared minus 3. Okay, so now I'm going to go below and look at the graphs. Now, these are accurate. These ones here are accurate appearances of the inverse functions right here. So this one, the first one here, we have y equals 1/2 x plus 4. It's this guy in blue. Here's y equals 2x minus 8, this guy in this orangish color right here. All right, these are true inverses of each other. Take a look. Tilt your head 45 degrees again. This one should look a lot more symmetrical. And if I pick a point like this one, 2, -4, there should be another point on this graph that's -4, 2, and it looks like it is. Or a point up here that's 5, 2, I think. Then there should be one that's 2, 5. Or where they intersect at 8, 8. This is 8, 8, that's 8, 8. And they should always intersect if they're going to pass through there in that way. So these are true inverses of each other. Let's find the domain and the range of our new guy right here, this guy that's going on forever like Zato. Okay? Well, this one's just like this linear one. It's a bit sharper, but its domain is still all real numbers. I can go forever to the left, forever to the right, and I will still get values out for this equation right here. I can still get my all reals. Range, same idea. I can go forever upward or downward. As long as I plug in the right values for x, I will always get certain values out for that. Okay? The second one here, my domain, now that I'm looking at this right here, my domain is now, again, trust these are inverses by the reflecting points. What values of x can I not plug into the square root? Anything that is negative. So this is my domain right here. X has to be greater than or equal to 0. The second I plug in a negative number for x, I will not get a value out for y. My range is a bit tricky here. Well, it's not tricky, but in the sense that we have plus or minus x here. If I plug in like 4 for x here, I can get 0 for y and -4 for y, which of course is based on those, is this a function or not, is the inverse. And we'll get on that later. The inverse is not a function, but that's okay. We can still take the inverse of the function. So it looks like the range does go forever upward here, and it does go forever downward here. So your range in this case is going to be all real numbers for this guy, because whenever I plug in for x, I'll get one up here and one down there. My last one, y equals x squared minus 3, when you think about this domain and you take a look at that equation, you're saying, well, I don't have any limitations on x. You say, I can do all real numbers here because no matter what I put in, I'm going to go ahead and square it. And then for my range, you'd have to then probably take a look at your graph. And now I'm going to take a look at the graph. And this was my original function right here, square root of x plus 3, right there. Here is the inverse one. Now, it makes sense that this is the inverse one given the look of the picture. But my question to you is, why is it not a full parabola like this thing says it should be? Why is this not looking like that right there? Okay. Well, the answer has everything to do with the fact that your original guy had a limited amount of points that it could have based on its domain or based on its range, what have you. Doesn't matter what it was. So this guy has to have the same kind of limitations. In what way? Let's take a look at the graph back for domain again. Apparently, it's not all real numbers, right? You can't go forever to the left. You have a stopping point right here at 0. You can let x be 0. You can let x be 0, but you have to make sure that it's greater than it as well, going in this direction. As this goes on forever up, it also goes on forever over. Despite the fact that it looks like you can plug in anything for x, you are handicapped based on your original function. So for your domain, x can only be greater than or equal to 0. And same with y. In this case here, it can be greater than or equal to apparently -3, because that's where the vertex is at for this guy. So taking a look at graphs is incredibly important for domain and range for the inverse of functions, but let's go ahead and tie in the domains and ranges that we just found here. Real, real, greater than or equal to 0, real, greater than or equal to 0, greater than or equal to -3. And let's take a look at what we originally found 2 slides ago. Real, real, real greater than or equal to 0, greater than or equal to -3, and greater than or equal to 0. What's the connection, because I don't have them on the same screen, what's the connection between these ones and the ones on the screen after it? They're the same, but anything that was in the domain before is now the range. Take a look at this. All real numbers domain, y is greater than or equal to 0. What's over here? X is greater than or equal to 0 here, and all real numbers. So anything that was domain has now become range, and anything that was range has now become domain for the exact reason that every x becomes a y and vice versa. Okay, so when you take the inverse of something, you're taking the inverse of a lot, of the equation, of the points, of the graph, of the domain, of the range. You're doing it for a lot of different things here. Okay, so that's where that thing turns out as well. So you don't necessarily have to graph them if you already know the domain and the range of your original function. You can then determine the domain of the range of the new function, because this is always true. The domain of the original function is always the range of its inverse. And the range of the original function is always the domain of its inverse. There are no exceptions. So the one thing that we had to really be careful with number 3 was identifying this domain from the get-go. Because the second that I identified it as such, my range immediately becomes that. Okay? Same with the range for this other one. As soon as you identify its range, your domain immediately becomes that. And it skips past that all real numbers thing. And that was huge. That was huge for this problem. We had to make sure that we established that from the get-go. So, you can have inverses that are not functions. As long as the domain and range are the same, then it's just going to be okay. The inverse is just not a function, and we'll deal with it. And we're going to talk about that a little bit here. And then also, your original one might handicap what your new equation looks like. Again, this is a quadratic, but there's a huge stipulation here. You have to make sure you're greater than or equal to 0. Okay, so all that other talk was good and dandy. Now I'd like to go on to some other talk here regarding something called the horizontal line test. Now, what's this whole thing about? Well, first of all, I'm going to ask you here what the inverse is of a horizontal line. And if you consider that this is the line y equals x, and this horizontal line here is y equals 5, okay, if we take the inverse of it, that means that x swaps with y. So there is another line here that's called x equals 5 that exists as a vertical line. And all it really means, it's about to be up here, but all that means is that anywhere there was an x, y value here will be swapped. X and y will swap, and we'll get them right here. Like the point 0,5 becomes 5, 0. The point -3,5 becomes 5, -3. And so on and so forth. Even 5, 5 is still 5, 5 here. But you can see this is going to be a horizontal line. A vertical line going up and down here. That's the inverse of this horizontal line. Okay. Now, if you consider this to be a function, because it is, it passes its own vertical line test. Notice how its inverse is not a function. This one's literally a vertical line. It actually fails its own vertical line test by being a vertical line. Some inverses are not functions, and we can determine whether they are not using. We can determine whether or not they are using the vertical line test, and I just did right here. A vertical line definitely fails the vertical line test. It's not whether it is a vertical line. The vertical line determines whether or not there are multiple y values for any single x value in your equation. The only x value in our equation here is 5, and there's an infinite number of y values, so it's definitely failing that. Is there a way to determine whether an inverse is a function without graphing it? And I don't mean without graphing the original function. I mean without graphing the inverse function. There is, and it does have to do with this horizontal line test here. If you consider the fact that the inverse of a horizontal line is a vertical line, and if you consider the fact that we use vertical lines to determine whether functions fail their own vertical line test, then do you think that we can do something with horizontal lines here and their inverses, and a regular function? So let's take a look here. We had these original functions here. Which of the following inverses are also functions? Well, using that good old vertical line test that we were talking about before here, if I drew vertical lines to represent, not quite, but if I drew vertical lines to represent whether or not these are passing the vertical line test, I'd say that these guys right here are doing just fine with the vertical line test. Both of them are passing it. Now, what I'm curious about is if a vertical line for an inverse function looks like that, well then, what is that inverse? Here's the blue. Its inverse would be a horizontal line. So what I could do theoretically is if I only had the blue function right here, I could determine whether or not its inverse would pass the vertical line test by doing a horizontal line test on blue right there, not on orange. You can ignore the orange for now. I just can't get it off the page there. So if blue fails the horizontal line test, then its inverse would fail the vertical line test. So if this graph wasn't here, I could still check that out. Here was an original function here in red, and then the inverse function in purple. As this purple function fails the vertical line test, that would also mean that the red is failing a horizontal line test. So if I never have this one graphed here, I don't have to graph it to see if it becomes a function or not. I could either tilt my head to the side 90 degrees and make these look like vertical lines, or I could simply draw horizontal lines and say that they fail that test. Now, I know I'm saying the same thing over and over. I do just want to make sure that I'm honing in on that in a very grand way, because I definitely want to hit on that point. And then this third one right here, also, I think the green was the original function there. So if this one passes the vertical line test, its own vertical line test, then its horizontal line test, then this guy here would pass its vertical line test. And they seem to do just that. So once again, just as I'm saying here, this vertical line, here, I'll make them different colors. This blue guy is showing that the turquoise, man, my color selection is not that great. See this guy right here? I'll call it teal. I don't know what color it actually is, but this tealish color here, it's passing this vertical line test no matter which set of points I go. Now this is the inverse function. This one here is the inverse function. Remember, this was that x squared minus 3, but its domain was x is greater than or equal to 0. So this already was a function, and I didn't need this one to be here if I only had this horizontal line for the original function. As long as it passes that, we're good. And again, I know I do realize that I'm saying the same thing over and over, but just the interaction, the visual, and the repetition with it, I think is really what I'm hoping to say there. Now, down below, I have those notes. An inverse is a function if the original function passes the horizontal line test. This one passes. This one fails. This one passes. Therefore, inverse is a function. Inverse is not a function. Inverse is a function. A function is said to be one-to-one if its inverse is also a function. So there's this idea, and there's this other new key term here called one-to-one. All one-to-one means is that every unique x value has its own unique y value. So as you can see, so if a function is one-to-one, then every x is only mapped to one y, which is true for every function. But also, if the inverse is a function, then every y in the original is also only mapped to one x. So let's take a look at an example that's not one-to-one, like this one right here. This is not one-to-one because there are multiple x values shared for any two y values that are greater than 0. At y equals 1, there are two x values here at -1 and -3. They each share them. at y equals 4, the values x equals 0 and x equals negative 4 are shared. And at y equals 9, the values x equals 1. Y equals 9, the values x equals 1 and x equals negative 5 are shared. So you can see that there are not unique x value. Let's see. There are not unique y values for every x value necessarily. And if you're looking at the inverse here, of course, it's not a function, and that also displays it. So this one's a one-to-one function. This is not a one-to-one function. This is a one-to-one function for the same very reasons as the horizontal line test and the inverses not being functions. Okay, let's do some examples, and I think I'm doing examples through the rest of the way pretty much here. Find the inverse of each function, sketch a graph to confirm. So what I'm going to do is I'm going to change f of x to y, and I'm going to do these pretty quickly because they're all going to be the same thing each and every time. F of x changes to y. I didn't change anything here. Now that I'm going to change my y to an x and my x to a y, things have changed. This is now technically my inverse function here. But I want to set it equal to y. So I'm going to move the 2y over here, subtract 5 from both sides, divide both sides by 2, and we will now get y equals x minus 5 all over 2, or inverse function equals, I'm going to write it as slope-intercept form because I know how to graph that a little better. 1/2 x minus 5 halves. Now, when we say sketch a graph to confirm, all that means is that if you sketch these graphs and they appear to be reflecting across y equals x, then it looks like all is good. So if I graph f of x first here as 2x plus 5, I start at 5 and I rise to run 1 like so, and I'm going to get this graph. And I'm going to be as perfect as I can here. I'm not going to draw rough lines or anything like that. I'm actually going to use the line tool and graph this one. So this guy, when graphed, looks like that there. Here's 1/2 x minus 5 halves. Now I'm not too pleased about actually having a decimal or a fraction y-intercept, but I'll still deal with it. Rise 1, run 2, like so. And on this way as well. And again, I'm going to graph this across y equals x, and what I'm expecting to get is that symmetry going across there. Now, the reason why this is right here with this 0, negative 2.5 is because there's a point here that's negative 2.5, 0. So don't expect them to always be decimals, you know. Expect them to kind of just be whatever they need to be here. So this green one should be an inverse function of that, meaning if I graphed now the line y equals x, in fact, let me just do that really quickly on all these graphs. If I draw a line for y equals x across right there, then I should tilt your head 45 degrees clockwise there, and you should see this symmetry going across here. And they should meet and intersect right through there. So that's going to be the case for all of these ones as I graph them, assuming I graph them correctly. So that graph kind of confirms this. It confirms everything that I've been looking for there. Okay, number 2, same idea. Y equals 3 minus x. Swap, x equals 3 minus y. Add y to both sides, subtract x from both sides. I'll get y equals negative x plus 3. So this I'll make green, this I'll make red, as I did last time. The original function, 3 minus x, is also the same thing as, wait a minute, that's the same thing as negative x plus 3. Is this the same thing twice? Negative x plus 3, and that's negative x plus 3. So let's see what we got here. Negative x plus 3 is starting at 3 up here, okay, and going down 1 over 1, down 1 over 1, etc. Here's my original function. And as I make it red, hang on. As I make it red and go down here, there's my original function. Now my inverse function is negative x plus 3 as well. So I took a look for 1 second. I was like, wait a minute, something wrong. And I realized, wait a minute, something's right. Same thing. If I plot all these points, try and think of what these points are. All right? I'm going to write some of them down. here's a point that is 0, 3. If this, well, here, let's pretend like this was the original function. Here's a point that was 0, 3 in the original function. Where is that point on the graph for the inverse? That point should be at 3, 0. Does that exist on there? Yes. How about the point 1, 2? Well, the inverse should have 2, 1. So all of these things are the same. They're reflecting in a different way, but they're the same graph that you get out. So this guy right here should also be green along with the red. Okay. Both of these actually are representing the same line. The inverse functions, this is as, I guess, is as one-to-one as you can get in that they are identical. They're reflecting across here because these points mirror each other. This point mirrors, it looks like, this point right here. Pretty cool. So that one confirms it. That one's pretty set up. Okay, y equals x squared minus 1. So x equals y squared minus 1. So y squared equals x plus 1. Take the square root of both sides. Y equals plus or minus the square root of x plus 1. So this one here is a square root graph, and I'm going to graph above and below the x-axis. The starting vertex here is going to be at -1. Well, actually, here, let me start with this one. This first graph here in red will start at 0, -1. Stretch factor is 1, so I'll go over 1 up 1, over 2 up 4, over 3 up 9, and reflect across my axis of symmetry. Not this axis of symmetry, but this axis of symmetry, right across here. Get the best looking graph I can possibly make by drawing it. And there's my initial parabola right there. This guy right here has a vertex at -1, 0. And its stretch factor is 1. And I'm going to go both above and below the x-axis here. So there, over 4 up 2, over 4 down 2, over 9 up 3, over 9 down 3. And I get this graph right here, which is not a function, but it's the inverse of a function, and it's still graphable. I may do that. And there you go. Once again, tilt your head to the side, as I'm doing right now, and you get, a little ink blot thing going on there, a little Rorschach ink blot test. All symmetrical. All's good. This is mapped 1-to-1 as need to be. And remember, this vertex was -1, 0. This vertex is 0, -1. You start to get the idea of that. Okay, I'm going to do, I think, 6 more problems. And we are going to only find the inverse, and then the domain and range. And then we're going to determine whether the inverse is truly a function. And you might have to do that by some representation. You might not be able to have the graph with it, but whether something's plus or minus, like this one, you understand the inverse was not a function here because I'm graphing 2 sets of lines. So I think it's more likely if you have a plus or minus somewhere with this, then it probably is not a function. But we can recognize some things with the domain and range without the graph itself for us to determine this. Number 1, the original function is 4 minus 2x. Now this is a linear equation. Its domain should be all real numbers. Its range, assuming that it has a slope that's not 0, it does, should also be all real numbers. Now I'm stating that right now because I want to also be cautious of that whole 1-to-1 idea, what the domain and range of the inverse should have been. Okay, so the original was 4 minus 2x. So the inverse is 4 minus 2y equal to x. Solve for y. I'm going to add 2y and subtract x. 2y equals -x plus 4. Divide by 2. I'll get y equals -1/2 x. Minus, or plus, hang on, let me get that x a little higher up there. Plus 2. So not y, let's put inverse function of. So there you go. There's the inverse function. Is the inverse also a function? Yes, it is. It's also linear, has no sort of issues going on there. Number 2, the original is The square root of 2x plus 12. Now, I can't take the square root of negative numbers, so I have to make sure that this inside set is greater than or equal to 0. And in order for that to be the case, x would have to be greater than or equal to negative 6. So my domain is exactly that. X is greater than or equal to negative 6. Range is a tricky one to work with when it comes to this kind of stuff, but if you understand where your vertex is in this sense, the vertex, if I substitute negative 6 into here, I'll get 0 out, not only for my square root, inside the square root, but also for y, for f of x. And it goes upward because this is a positive, so y will be greater than or equal to 0. Feel free to graph it if you may, but this is a square root graph that would be looking like this right here in some fashion, in some capacity there. Is it a function? Is the original a function? Yes, the original is a function. And let's also test the inverse. Oh, it's determined whether the inverse is truly a function. My bad. But I believe that this actually might be a function as well. But I'm sorry about that. This one was a function, yes, and this one was a function, yes. So I will not circle yes until the very end. My apologies for that. So this is y equals the square root of 2x plus 12. So swap x and y. X equals the square root of 2y plus 12. And start solving for y here. Square both sides. I'm going to get x squared equals 2y plus 12. Subtract 12. Move the 2y over here. Divide both sides by 2. I'll get y equals 1/2 x squared minus 6. Okay. Now, given this 1/2 x squared minus 6 right here, there's also something about domain and range that I have to keep in mind when I'm taking the inverse. If this range is y is greater than or equal to 0, then this domain is x is greater than or equal to 0. So if I were to graph this thing, it would only just be going up, that kind of fashion. It wouldn't be a full parabola. It would just be a half parabola. So that's one thing to pay very close attention to when it comes to finding your final inverse function like so. Now, is this one a function? Yes, it is. This one has no plus or minus issues or anything like that. It's just a half parabola going upward. So it still is. My apologies once again for doing what I did there. Okay, so this last one here. F of x equals 2x squared minus 4. The domain should be all real numbers. I should be able to plug anything in there. In my range, I want you to think about where this vertex is going to be. It's going to be at 0, negative 4. It goes upward, so y can be greater than or equal to negative 4. Now, the original is a function. All of these actually will be functions. They're all f of x. So my stupidity actually really did kick in when I was circling too early on. Let's go ahead and find the inverse of this function by swapping x and y and then solving for y. Okay.
I didn't quite understand that.
I just made Cortana pop up somehow. I'm not quite sure what I just did. That was pretty interesting. Solve for y, so 2y squared equals add 4 to both sides, x plus 4. Divide by 2. We'll get y squared equals 1/2 x plus 2. Take the square root of both sides. We'll get y equals plus or minus the square root of 1/2 x plus 2. Okay. So f of inverse function is the exact same thing. Equals plus or minus the square root of 1/2 x plus 2. Now, something to keep in mind here, although it looks like you'd be able to figure it out any sort of way, your domain for this guy is that x is greater than or equal to negative 4 for the very fact that y is greater than or equal to negative 4 here. But see if that works. If I substitute negative 4, what do I get? Half of negative 4 is negative 2. Negative 2 plus 2 is 0. Looks like negative 4 is the smallest value for x I could possibly get out, so that seems to match. Now, is the inverse a function? Keep in mind what the original domain was, all real numbers. So if this guy's range is all real numbers and there's no limit, it looks like I can go plus or minus in the square root function, which would be a sideways parabola like so. This guy is not a function in that sense because it's failing the vertical line test here, which was also failing this guy's horizontal line test. Remember, this parabola here would have failed its horizontal line test for the same reasons I mentioned there. Last 3, 4, 5, and 6, and then I'm done. Let's go ahead and use black. I haven't used black yet. Same instructions, just 3 more sets of problems. Linear equation. Domain all real numbers. As long as the slope's not 0, the range should also be all real numbers. So y equals 1/2 x minus 8. Let's go ahead and swap x and y and calculate the inverse in a more proper fashion. So it looks like inverse function of. Solve for y. X plus 8. Multiply both sides by 2. We'll get y equals 2x plus 16. So inverse function is 2x plus 16. This is a linear equation, no domain or range restrictions. Looks like this will also be a function as well. This next one here is a square root, so just like the other square root there before, we have to be very cautious about our domain. This guy must be greater than or equal to 0 inside the square root. Therefore, x has to be less than or equal to 4, like so. And that makes sense. If you make something that's greater than 4, then I'm going to be doing 8 minus a number that's greater than 8. And I don't want that. I don't want a negative number there. Range, same idea as normal here. This is a positive square root. But this time, it's going to be, not something about this time. This time, my square root function goes to the left, but it still goes upward. So if I choose my rightmost bound here at 4, looks like I get 0 in the square root, which gives me 0 for y. My y value would be greater than or equal to 0 in this case. Now let's go ahead and find the inverse of the function, and let's make sure that we are very careful about this range is going to be this other guy's domain. Be very, very cautious about that when all said and done. So y is the square root of 8 minus 2x. Therefore, in the inverse, x is the square root of 8 minus 2y. Apply all your inverses now as a result here. Square both sides. And we will now get x squared equals 8 minus 2y. Continue to solve for y. Add 2y to both sides. Subtract x squared from both sides. Divide by 2. We will get y equals negative 1/2 x squared plus 4. So the inverse of the function is negative 1/2 x squared plus 4. Okay? This right here, let's see what I wanted to say about this. The range for this one, y is greater than or equal to 0. For the domain for this one, x is greater than or equal to 0. So this is an upside-down parabola that looks something like this right here, where x can only be greater than or equal to 0. The other half will be missing here. This one is also a function. It passes its vertical line test as the square root function would have passed its horizontal line test. This one is indeed a function. Final problem, then all said and done. F of x equals 8 minus 4x squared. This is a parabola, an upside down one to boot. I can plug in anything for x there. Range, let's be a little bit careful. I'm going to go ahead and rewrite this thing so it says negative 4x squared plus 8. The highest this thing goes is if I made this thing 0, because any other value for x here would make this thing go lower. So if I plugged in 0 for x, I'm going to get 8 for y, and this thing goes downward from there, so y can be less than or equal to 8 for that one. Again, range is really hard to come by with equations. It's really easy when you work with the graph, right? And you can always graph these ones. So we start off here in terms of finding the inverse by changing this into a y, swapping out x and y. Now we're at our inverse equation. Let's go ahead and solve for y with this guy. Add 4y squared to both sides. Subtract x from both sides. Actually, I'll make this 8 minus x. If it's a square root one, I'd prefer to have the constant first. I think books do as well. Y squared is 2 minus a quarter x. Therefore, take the square root of both sides. Y equals plus or minus the square root of 2 minus a quarter x, like so. Now, plus or minus because of the square root guy, but make sure that this domain was all real numbers. It was, therefore this range can be all real numbers, so we can do both plus or minus there. This one has a certain provision here that x has to be less than or equal to 8. Let's see if that makes sense with what it is we had to do here. If that's true, let's see this domain. 2 minus a quarter x had to be greater than or equal to 0 to stay positive inside the square root, or 0. So 2 had to be greater than or equal to a quarter x. Multiply both sides by 4. x had to be less than or equal to 8, which also agrees with that right there. So make sure you really trust that that domain and range flips like that. Now, is this a function? Well, no, because this is an upside down, not an upside down. This is a sideways parabola that's going actually to the left. That negative x actually has to do with that going to the left there. And I don't know what the exact graph looks like. I'm just giving you that idea. Failing its vertical line test, just like the original quadratic right here would have failed its horizontal line test. So this is not a function. Okay, I do have one more set of problems here, so I lied about what I was talking about before. Composition of inverse functions here. What a composition of inverse functions says, if you apply a function to its inverse, okay, or an inverse to its function, then you are just getting back out whatever value you were taking the function or inverse function of, okay? The function of the inverse function of x equals x, and the inverse function of the function of x also equals x. Okay, all that means is that you're getting back out what you first put in originally, because these guys cancel each other out. Just like multiplication and division cancels each other out, just like addition and subtraction cancels each other out in its own unique way, this also cancels each other out in its own unique way, and you're left with whatever's there. Now, don't take my word for it. Let's go ahead and prove it in such a way. For the function f of x equals 10x minus 10, let's go ahead and find the inverse function of the function of 30. Now, you might be thinking in your mind the answer is 30. And you know what? You wouldn't be wrong. However, you might have to verify it as well. And I have a couple ways I can verify this thing. I'm going to start by taking a look at just this way in itself. I'm going to take f of 30. Well, actually, here, before I do that, I need to find the inverse function here. Y is 10x minus 10, therefore x is 10y minus 10 for the inverse. Solve for y here, add 10 to both sides. You'll get x plus 10. Divide by 10, y equals either x plus 10 over 10, or if I were to graph it, I'd probably write it as 1/10 x plus 1. Both the same thing. So the inverse function here, I'm going to go ahead and deal with this one, x plus 10 over 10, because I will not be graphing this. So there's my inverse function. Okay, I'm going to take my inverse function there and make sure that I use that for whatever I find f of 30 to be. So I can go ahead and take the f of 30. F of 30 is 10 times 30 minus 10, which is 300 minus 10, which is 290. Now I'm going to take this output 290 and I'm going to substitute it into my inverse function here, right? If I take the inverse function of the function of 30, I will now be taking the inverse function of 290. So the inverse function of 290 is 290 plus 10 all over 10, which is 300 over 10, which is 30. Nice. So I got it back out there. Now what I will not do is I will not take the function of the inverse function of 30. However, I'm going to now just prove it just by doing this algebra here. I am going to take the function of the inverse function of x, and I'm just going to show you that that one's x. But I did want to show you, I don't know why that one's still there, but I did want to show you, however, using an actual number example, because I think that people really like number examples as things, because they like to feel good about what it is they're doing. Sorry, I'm trying to clear this out. This should not be here. Okay, so let's go ahead and try to do the inverse, the function of the inverse function of x. And let's see that we actually do get x right back out here. So the function of the inverse function of x says that I'm going to take the function of this, x plus 10 over 10. Which means x plus 10 over 10 takes place of x in this equation here. So, let's see if I can fit that all on one screen. That'll be 10 times x plus 10 over 10 minus 10. It's quite a bit of tens. 10 over 10 is 1. So you just left with x plus 10 here. Minus 10. Inverses cancel out equals x. So you are just left with x each time. First, this one's more of a proof, more or less, and with an example, and this one's using an example with a number right there. So you're still getting the same stuff out. So you take the inverse function of the function of something or the function of the inverse function of something. You're just left with that something that you were looking for. Kind of sweet. Okay, now I'm finished. So everything that was covered in this section, we found inverse functions informally and verified that two functions are inverses of each other. Okay, so the way that we went about that was just by taking a look at its symmetry, right? We try to make sure that everything just mapped to itself and that they possibly intersected even at y equals x. All right. How to verify graphically and numerically that two functions are inverses of each other. I take that back. This is the graphically part right here. Numerically, we would do it just by seeing that x's became y's and y's became x's. Use graphs of functions to decide inverses. Okay, so you could then map points over by doing that. You could also do the horizontal line test and such to decide whether inverses were functions. And how to find the inverse functions algebraically, swap x for y in the equations, and then solve for y again. Fiend!